Have you ever watched something move and wondered if you could predict its future? Well, today we're going to do exactly that. We're going to solve a classic physics puzzle about a motorboat that's slowing down, and our secret weapon is going to be calculus. Let's get right into it. So picture this. A motorboat is just coasting along, the engine's been cut, and it's slowing down. The big question, the mystery we're trying to solve is this. Can we figure out the exact moment it's going to drift to a stop and exactly how far it's going to travel before it does? It's like a little physics detective story, and we're about to crack the case.
All right, let's get into the specifics of our motorboat's situation. We know it starts out at a pretty steady speed, and then it starts to slow down. And the real key here, the most important clue, is that we have the exact formula for how it's slowing down. Okay, so these are the two pieces of the puzzle we have to work with. First, its starting velocity is a solid 5.0 meters per second. And second, we have this function for its acceleration. Now, look closely at that formula. See the t in there? That is so important. It means the boat's deceleration isn't constant. It actually gets stronger and stronger the longer it slows down. And believe it or not, with just these two facts, we have everything we need. Now, before we tackle our problem by working backward, let's just do a super quick review of the forward story of motion. You know, the way we usually think about this stuff. So it usually works like this, right? If you know an object's position at any given time, you can figure out its velocity just by looking at how fast that position is changing. That's a derivative. Then, if you look at how fast the velocity is changing, boom, you get its acceleration. It's a really clear one-way street. Position leads to velocity, which leads to acceleration. But here's the twist in our motorboat mystery. We don't have the position to start with. We're starting at the end of that road with acceleration. So we've got to figure out how to drive the wrong way up that one-way street, all the way from acceleration back to position. So the big question is, how on earth do we do that? If taking a derivative moves us forward, what's the mathematical tool that lets us hit rewind? How can we possibly reconstruct the entire journey just from knowing how it was slowing down from moment to moment? And the answer, the magic key, is integral calculus. Now, don't let the name scare you. Just think of it like this. If a derivative is like glancing at your speedometer to see your speed at one single instant, an integral is like adding up all those tiny little moments to figure out the total distance you've traveled. It lets us rebuild the entire story by summing up all the small changes. And this chart just lays it out perfectly. The forward path, with derivatives, is all about breaking the motion down. The backward path, with integrals, is all about building it back up. It's literally the rewind button for physics. Now, these are the two main recipes we're going to be using. The first one tells us how to get velocity from acceleration, and the second one tells us how to get position from velocity. But what's that little plus c tacked onto the end of each one? What's that all about? Well, that mysterious c is called the constant of integration. And it's not as scary as it looks. It's basically a placeholder for a missing piece of information. See, when we integrate, when we rewind, we know the shape of the motion, but we don't know the starting point. So we have to use our initial clues, like the boat's starting speed, to solve for c. It's the piece that locks our math into the real world. Okay, enough theory. We've got our clues, we've got our tool. Let's get back to that motorboat and finally solve this thing. All right, first things first, we need to find the boat's velocity at any given time. And to do that, we take the integral of our acceleration function, which, if you remember, was -1/4 t. This is our first big step backward. So we do the calculus, and we get this equation for velocity. But we still have that unknown c. How do we find it? We use our first clue. We know that at time 0, the velocity was 5.0. So if we plug t equals 0 into our equation, that whole first term just disappears, and we're left with v of 0 equals c1. And since we know v of 0 is 5.0, well, c1 has to be 5.0. Just like that, we have the complete, perfect formula for our boat's velocity. Okay, now that we have this powerful velocity function, we can answer the first part of our mystery. When does the boat actually stop? Well, think about it. A stopped boat has a velocity of 0, right? So all we have to do is set our brand new velocity function equal to 0 and solve for the time t. We just do a little bit of algebra, and there it is. The boat comes to a complete stop at precisely 6.3 seconds. First part of the mystery? Solved. But we're not done. Now for part 2. Where does the boat stop? To figure that out, we have to take another step backward. We're going to do the exact same process, but this time we integrate the velocity function we just found And after we integrate, we get this amazing position function. Now, technically, there's another constant of integration here, a C2, but we're going to assume the boat started at position 0, which makes that constant 0 as well. So this equation you see right here, that is our treasure map. It can tell us the boat's exact location at any time we want.
And now for the grand finale. To find the total distance the boat traveled, all we need to do is take our stopping time, 6.3 seconds, and plug it into the treasure map, our position function. And we get 21.1 meters. That's it. That's how far the boat drifted before it stopped. Our mystery is completely, totally solved. So, yeah, we solved a little puzzle about a boat. You might be thinking, okay, cool, but who cares? Well, it turns out this principle, working backward from acceleration, is one of the most powerful and fundamental ideas in all of science. This isn't just for boats, not by a long shot. This exact same method is used to guide spacecraft across the solar system, where being off by just a tiny bit can mean missing a planet by millions of miles. It's how engineers design roller coasters that are both thrilling and perfectly safe. It's how you can predict the arc of a thrown ball, and it's even how we analyze the majestic, sweeping orbits of the planet. So it leaves you with this incredible thought. We started with just a tiny bit of information, a simple formula for a boat's changing speed, and from that, we were able to reconstruct its entire journey through space and time. It really makes you wonder, if we can know an object's acceleration, what else can we predict about the motion of our universe? What other cosmic mysteries are just waiting to be solved? Thanks for digging into this with me.